Professor, welcome, Professor. Professor.
Hello, I'm here. I didn't
Professor.
understand about the Zoom link, but now I find it. Okay.
Yeah. Welcome, Professor.
Thank you.
Good morning.
Nice to see you.
There
Nice
it
to
is,
see everyone.
8 o'clock now. Good morning, Professor. Meet my colleague, Dr. Subramaniam, sir. Sir, Subramaniam, sir.
Yes, sir. Yes, sir. Hi, Professor.
Hello. Nice to see you.
Good evening, Professor. Welcome.
Yeah. Thank you.
My warm
Professor,
welcome to our FDP. Thank you for accepting our invitation, Professor.
Yeah, very happy to do that. Very happy to be here.
Professor, one more colleague is there, Professor Dr. Veena.
Hello, sir. Sir, good
Hello.
morning, sir. Good morning, sir.
Hello, nice to see you.
Yeah,
Thank you
yes,
for
sir.
the greeting.
Welcome. Welcome, sir. Welcome, sir.
Thank you.
Thank you. Thank you. Sir.
Ma'am, sir came, ma'am.
Good evening. Good morning, Professor.
Yes.
Good morning.
Good morning to you.
Yeah.
Nice
Thank
to
you.
see you. Thank you
Yeah.
for the greeting.
Yeah. How are you?
I'm fine. Thank you for the invitation.
Thank you. We have to thank you for sparing your valuable time with us.
Oh, I'm happy to be with you.
Happy.
How, Professor, what is the situation there, Professor? This pandemic situation? How
The
it is?
situation. Oh, COVID. Oh, unfortunately, that's not really too good.
Oh.
Yeah, in the community, there's quite a lot of that, I think, including some students of the university have that. I have a vaccine myself, so I feel a little safer, but in general, the situation is what it is. It's not perfect. It's sad, the situation. And for you, it's okay, or it gets better, or what?
Yeah, better, Professor. We made the students to come to college offline. Classes we have started.
Okay.
Going on. So here, 70% of them has been vaccinated.
Oh, that's good. That's good. For us, only about 50%. It's not enough, I think.
So you people are working at home?
We have a hybrid model. So the classes we have in the university, and so some activities in the university and some at home, like that. Mixed.
But they have opened all malls and everything. They have opened. Like it's all closed, sir.
So most things are open, but many things have some rules about you know, like how many people or things like that. And it's not uniform. In different parts of the country, it's different. So each town has some different rules. It's not centralized very well. But the situation is not really good. It spreads. This disease is spreading.
Yesterday we had talk by Paul Horlock. He gave a talk.
Yeah, good. So do many students join?
Yeah,
Do
they will
students-
join, Professor. They are joining.
Oh, that's great. That's wonderful.
Nearly 150 people will join, Professor.
Oh, that's wonderful.
Professor, we in our department we have organized many programs. So shall I pose? Shall I play the video? Small video for 5 minutes.
It's up to you. Fine.
Shall I start? Shall I start?
Yes, ma'am.
Yes.
Good evening to all. I welcome you all for day 9, session 11 of 2-week International Faculty Development Program on Advanced Computational and Experimental Research in Physics 2021, organized by Department of Physics, SRM IST Ramapuram campus. SRM Institute of Science and Technology is one of the top-ranking universities in India with over 38,000 students and more than 2,600 faculty members across all the campus, offering a wide range of undergraduate, postgraduate, doctoral programs in engineering, management, medicine, health sciences, and science and humanities. The institute has academic tie-up with leading foreign universities like MIT, University of California, USA, University of Dundee, Oxford University, UK. Our institute is accredited by NAC with A++ grade in the year 2018 and got placed in A category by MHRD. With this, now I request Dr. L. Sudha, Professor in Ed, Department of Physics, SRM IST Ramapuram campus, to give the welcome address. Ma'am, please.
Yes, thank you, Dr. Beena. Good evening, all who have joined this 2-week International FDP organized by Department of Physics, SRM Institute of Science and Technology, Ramapuram campus. I take great privilege in welcoming Dr. David J. Singh, Professor, Department of Physics and Astronomy, University of Missouri, Columbia, USA, who is going to deliver a talk on understanding thermoelectrics and their performance. Thank you, Professor, for joining this 2-week FDP, for sparing your valuable time with us. Thank you. Thank you for accepting our invitation to deliver a talk. And I extend a warm welcome to all the other participants from different colleges, institutes, and universities from India and abroad. Have an enjoyable learning. Thank you.
Okay. Well, first of all, I want to express my feelings about being able to spend the time with you this morning and how happy I am that I have this opportunity. I really am delighted to be able to speak with you today and to share some of the work about thermoelectrics that I can share with you for this time that we have together.
Professor, sorry to interrupt you, Professor. 1 minute. So I'll introduce you, Professor, to the participants.
Oh, I'm sorry. Go ahead, please.
It is my great privilege to introduce Dr. David J. Singh, Professor, Department of Physics, Astronomy, University of Missouri, Columbia, USA. So he completed his PhD in University of Ottawa in Canada from 1985 to 1988. He completed his postdoctoral appointment at its College of William and Mary. In 1988, Singh sir joined the theory group at the Naval Research Laboratory in Washington, D.C. In 2015, he joined in the University of Missouri. Now he is a Curtin Professor in the Department of Physics and Astronomy. He has more than 500 publications in his credentials. His area of research is in condensed matter physics with a focus on electric structure materials, ferroelectrics, thermoelectrics, and iron-based superconductors. He has contributed to the application of density function theory, especially to iron-based superconductors and methods. Sir's awards and credentials are: he is a fellow of American Physical Society in 1997. He was an editorial board member of the New Journal of Physics and Scientific Experts. He is also a fellow of Royal Society of Chemistry. He received the Evo Halbert Annual Science Award and the Gordon Battle Prizes. His credentials are big. So due to time constraint, I've stopped, Professor. I welcome you to this session, sir. Take over the session, sir. Thank you so much.
Okay, thank you. I really appreciate being here with you. I thank you for the invitation, and I especially thank all the students and young people in the audience for taking the time to spend some time with me and to hear me speak. I'm really happy to be with you, and I'm really happy to be able to give this talk. So let me go to the full screen mode, and then let's go. So I'm going to start from the beginning and talk a little bit about thermoelectric materials. I suppose you can see my screen in full screen mode. Is that correct?
Yes.
Yes, Professor.
Okay, very good. So you may wonder what are thermoelectrics, because I think that's the first thing that we need to discuss. So I made a little cartoon to show it, but the cartoon, before you think too much about this cartoon, I just want to think about everyday life in the lab. So in everyday life, I want you to imagine that you have some container that
Slide
contains
is not
some
moving,
gas.
Professor.
I'm sorry, yes?
Slide.
Slide is what? Not, you can't see?
We are able to see understanding thermoelectrics and their performance.
That's perfect. Thank you. So just imagine a container full of gas. And in this container, you apply some temperature gradient. So you heat one side of your container. And then imagine what happens is that the gas becomes less dense in the part of the container that's hot. It's not an equilibrium property because it's there's a temperature gradient. So it's not a thermal equilibrium. But still, you can easily understand that the gas becomes less dense on the hot side, and the gas molecules accumulate at the cold side of the tank. So this is something we can imagine. And now we just make it a little bit more abstract. And we think instead of having a container of gas, we think of a semiconductor, and a semiconductor that's doped so that there may be electrons or holes inside the semiconductor. And so that's what this cartoon is about. So there's N-type semiconductor, which has electrons, and P-type semiconductor that has holes. And we have a hot side and a cold side. So there is a temperature gradient. So now you just imagine the same thing. And so it becomes a little bit intuitive then to think, okay, so the gas particles, in this case, the carriers in the semiconductor, become more dense at the cold side. They run away from the hot side and go to the cold side. And so then you have a cartoon like this, where the carriers are trying to accumulate near the cold side. Now the difference from the gas in the gas cylinder is that these carriers have charge. And because they have charge, then there will be an electrical field that they produce if they accumulate. So there will be a voltage. And this voltage is the thermoelectric effect. This is the Seebeck voltage that we're going to talk about. And so just you can see I made a little cartoon of a device here where you have N-type and P-type. These are electrical contacts. They are connected in series. So the electricity could go the way my arrow is going on the screen. And then across the device, you will have a voltage due to this temperature gradient. And so it's a way to connect electricity and heat. And so you can imagine then you can connect a load. And with this load, you can extract some power. And this power could be useful for something. So that's what the whole story about thermoelectrics is about. Nothing more than that. So if you understand that, then you can see that this is an effect that could potentially have some use. But then of course the use depends on the material. Like these are semiconductors, so there are different semiconductors. So the question becomes, what semiconductor should I use? And of course, if you want to have a heat source and extract some power, then you will probably be concerned with the efficiency. And it turns out that the efficiency of a thermoelectric device depends on what the material is that you choose. And so you should find the best material that you can use and then use that and make the thermoelectric device. And so there is a so-called figure of merit. This is called ZT, and it's some combination of transport quantities. The combination is electrical conductivity Electrical conductivity is important because we're going to have a current flowing through this device. And so if the conductivity is high, that means the current will easily flow. S is a coefficient called the Seebeck coefficient, and it tells you how much is the coupling between heat and electricity. For some materials, you may get a tiny voltage. That means the Seebeck coefficient is small. The voltage is proportional to S. For other materials, you may get a large voltage. That's better. So there's S squared. There's a factor of temperature that makes it dimensionless. And in the denominator, you have kappa. Kappa stands for the thermal conductivity. And you can imagine why it's there. It's because if you have some temperature difference and the heat flows easily, then the heat is lost and you can't use it. So that's why there's a kappa. So before I go on, I just want to mention I have many coworkers and I list some of them. So the things that I'm going to discuss were done with these coworkers, and so I don't want to forget them. All right. So what is the what is that good for? So I said maybe you can use that. So let's look at some of the things that you can use that for. And so this is a historical example. This is a spacecraft. When I was a young person, I was very inspired to science by these spacecraft. I thought it was amazing that we could launch spacecraft into outer space and that men could go into space, and women too now. And I think this is a wonderful thing, and it was very inspiring to me as a young person. Maybe to young people nowadays other things are inspiring, but to me this was a very inspiring thing. And so this is a spacecraft called Voyager. Voyager was the first human-made object to leave the solar system. That was quite recently. And the reason we know that is Voyager still functions. There are 2 Voyagers that have left the solar system already now. And it still functions because it still has electricity for the instruments to work and to send a signal to Earth. And how is that? There's no sunlight in the distant parts of the solar system and outside the solar system that you could use for photovoltaics. So the source of power is nuclear, and the way it works is that there is some nuclear material. This is the generator of Voyager. Inside there is some special isotope of plutonium, and that decays naturally and produces heat. And that heat is converted to electricity by thermoelectrics. And the thermoelectrics inside Voyager are made of a material called silicon germanium. It's a semiconductor alloy of silicon and germanium. And the reason that this works so well is because what I showed you was a semiconductor device. So there's no fluid and there's nothing that moves. And so you can imagine that it can be made very reliable. And that's why Voyager continues to work for tens of years. Now, today we think about efficiency in a different way. So we think about climate change and the importance of maintaining a proper balance between human prosperity and energy use, and try to reduce the energy that we use, but at the same time keep the prosperity of society, which is important also. And so we think about how to make things more efficient. And so this is a chart that I got from somebody at an automobile company, General Motors, which is an automobile company in the United States. And it's showing a sort of a schematic of what might happen in a car. And so the idea of a car is you burn fuel and then you drive the car. And so the efficiency is how much energy goes into driving the car compared to how much energy was in the fuel that you burn. And the difference is various losses. And so they think about the losses. And so the losses are in the form of heat. And here's some approximate rough numbers, estimates of how much those losses are. And it's important to realize that about 1/3 of the energy goes into driving the car. That's a good situation. It's not usually that good. And about 1/3 goes into the exhaust. And what you might know is that the exhaust is quite hot. And so if you could recycle some of this heat to drive the car, then you could improve the efficiency of the car. For example, suppose you could get 10% of the heat in this exhaust gas and convert it to electricity that could be used to drive the car, then you could improve the efficiency by 10%. And so people thought about thermoelectrics as one way to do that. And thermoelectrics could be an important way to do that because they can scale to small power. So the amount of exhaust gas that you have. And then what you realize is there's a problem. And the problem is that there's this ZT parameter that controls the efficiency. And for the materials that we have, the result would be low efficiency, and this application will not be successful. And so people think about thermoelectrics and how to make better materials that would be giving higher efficiency and could enable applications like this that could be important for society. So now I want to show some slides that are a little bit more technical. And I want to start with a formula that the students have seen in their classes very frequently, though they may not immediately recognize it. So this is that the energy is the square of the momentum divided by 2 times the mass. And this you have seen in your early physics classes, right? For classical objects moving, then we know that the kinetic energy is the momentum squared divided by 2 times the mass. And in quantum mechanics, that becomes h bar squared k squared over 2m. It's the same formula. And what that looks like is a parabola. So if this is energy and this is momentum, then the energy looks like this. It's a parabola, right? And in the semiconductor, we think of the energy of the electrons as a function of the momentum, but we use k as a parabola. And this is the so-called parabolic band model of semiconductors that some of you might have heard of. And the idea is that if you dope a semiconductor, then there are electrons up to a certain Fermi energy, and so this is called the dispersion. And the problem with that is that, although I'm not going to show it explicitly, if you have this parabolic dispersion, then it's very hard to get a high ZT, because it turns out that if the electrons have a low mass, and they have an effective mass in semiconductors, so this can be different in different materials. If they have a low mass, then they move easily. Light objects move easily. And if they move easily, that means that the conductivity can be high. But unfortunately, the Seebeck coefficient, which is also called the thermal power, depends oppositely. And so if they have a light mass, then the thermal power will be low. And in the ZT formula, we had a product, and so that just doesn't work out. And the fortunate thing for us is that real semiconductors could be more complicated. So this is a real semiconductor. This is gallium arsenide, and it shows that actually the dispersions could be more complicated. And what we're going to see is that we can use these more complicated type of dispersions to produce good thermoelectric materials. So before I do that, I want to just say a few words about, okay, we saw the impact for society perhaps, but why else will a physics student or a physicist or a chemist be interested in thermoelectrics? So the reason is that thermoelectric performance is what we call a contraindicated property. What does that mean? So that means what I just showed you is that if you take the standard model that you read in the textbook, that's the parabolic band model, there's no such thing as a good thermoelectric because the properties go oppositely with mass, and so there's no way to find a proper mass because it just doesn't work. And still we want to find good thermoelectrics. Well, and so it's interesting. Why is that interesting? If you're studying a contraindicated property of matter, the textbook model doesn't work. And so you must think about more complicated and perhaps more interesting ways to go around these contradictions. And it's possible, but then you have some interesting physics to do. Another aspect which is important is that if you have a contraindicated property And then somebody shows you a material and says, by the way, this material that I found, it has a high ZT. And you know that ZT is a contraindicated property. Then you should study that material. And why should you study that material? You should study that material because that means, since it has a high ZT, that there is some unusual physics, and you may discover some unusual and interesting things in that material. So it will be an interesting material to study. So that's the reason that I find thermoelectrics so interesting. Here on this slide, I just list some of the contradictions involved in finding high ZT, and I'm not going to spend time on this because we're going to see some of this later. But I just mentioned that, I just list some things because those are ways that people find to go around these contradictions. And I feel that's one of the rich aspects of thermoelectric materials. So here's something, here's a puzzle. I'm going to come back to this puzzle. So recently in physics, topological phenomena get a lot of attention. It's a recent and interesting subject. And this is a list that I took from a review article, a part of a list. It's from a review article by somebody named Ando, published in 2013, so 8 years ago now. And it's a list of known topological materials at the time that this review was written. And what you see is okay, it's a list of materials. And what it's a list of is a list of known topological insulators or topological materials. And okay, so it's a list. But the interesting thing about this list is most materials are not topological. So these are semiconductors, and it's a small subset of the semiconductors. But a person who works in thermoelectrics would look at this list and see that these are thermoelectric materials: bismuth selenide, bismuth telluride, antimony telluride, this one, 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 this one. Not all, but many of them are the good thermoelectric materials, which are also a small class of semiconductor materials. And so there's a big overlap. And that relates to what I was talking about, and we'll see why. So I also want to mention that, you saw Voyager and you saw me, and you saw that I have white hair, which means that I'm not so young anymore. And so you realize that when I was talking about my childhood and how these spacecraft inspired me, you realize that must have been a long time ago. And so thermoelectrics are not new. And so this is and so there are books written on thermoelectrics from long ago, as you can see. And one of the things that was realized long ago is that it's important to have the proper amount of electrons. So that's like the proper amount of gas in your gas cylinder, to make the analogy with the first slide. In order to get the right balance between conductivity, you need electrons to conduct, and Seebeck coefficient, which in this book, I just copied the book, it's called alpha instead of S, but that's the same as S. There is some proper balance as a function of the number of electrons or the doping level. And so this is S squared sigma, the denominator, the numerator of ZT, and you see it has a maximum somewhere. And we want to find that maximum. And so experimentally, we can make some samples and test them, but that takes time because each sample has to be synthesized, or we can use theory. And so now we can use theory. All right, there are some formulas. I won't go through these formulas, but I want to say that there are some computer codes that implement these formulas. And the important thing is that nowadays with computers, we can calculate the band structure of semiconductors with approximations, but we can calculate them. And with those band structures, we can calculate the Seebeck coefficient and other transport quantities directly. And so these are just showing some formulas that are used. I don't want to spend time on these formulas, but I just want to say that they exist and you can find them, and they are in codes that you can use. So instead of that, I want to start with a certain material, because this is a known good thermoelectric, and so we can expect something interesting here. And this is a rather simple structure, and so it's easy to talk about in some sense. And so the compound is called lead telluride, PBTE. It's a material that was known since the 1950s. It was not used in Voyager. Voyager used silicon germanium, but it was used in other spacecraft. So Pioneer and some Apollo missions used lead telluride. And because of that, we have to say it's an industrial material since the 1960s. And what's interesting is that the ZT of lead telluride is less than 1 in its industrial form. But in the last 10 years or so, there have been several developments of lead telluride that show much higher ZTs, which says that there's something about lead telluride that was not appreciated in the 1960s that we are learning about. And so I want to spend some time using lead telluride as an example. And so I told you we can calculate those dispersions. And so these are calculations of those dispersion relations. Remember, it was a parabola. I showed you the ideal case, and then I showed you a more complicated case of gallium arsenide. So this is what you get if you calculate the so-called band structure of lead telluride. So this is K. It has different directions because we can work in 3 dimensions here. It's cubic. And this is the energy as a function of K. And okay, there's a maximum here, and we're going to talk about p-touch. We're going to talk about this part of the electronic structure where my arrow is. And you can see that it has a maximum at a place called L in momentum space or K space. And it doesn't really look like a parabola. Okay, so it's not a parabola. And actually, if you plot the density of states, which as I showed you for a parabolic band in 3 dimensions looks like a square root function, it doesn't look like a square root function. It's low, so 0 is here. And then we go to higher binding energy as we go down. And then it goes up sharply at some binding energy, about 0.2 volts. And what's going on is that if we plot it in 3 dimensions, then if we imagine the surface defined by where do you cut? So if I take some energy and I cut across, I take some constant energy, it cuts these curves. And so I plot in 3 dimensions where are the crossing points. That's called an isosurface. Then it looks like this. There are some pockets near that place where the maximum was. And then as I go to higher binding energy, go down, those pockets interconnect, and I get these tubes. And these tubes are what cause this upturn. And so that also has an effect on the Seebeck coefficient, which we can calculate. I told you we can calculate as a function of temperature. So this is temperature. And this is the value of the Seebeck coefficient. And it depends on the number of holes, in other words, the doping level, as we discussed. And so these are 3 different curves corresponding to 3 different doping levels in units of holes per centimeter cubed. And so what you see is that as you get some curves, they're fairly close and they have a certain shape. They increase with temperature, which is quite normal. And this is some experimental data. And the experimental data agrees very well with the theoretical curve, which you might think is sort of uninteresting. But it is interesting. And the reason it's interesting, this was work from 2010 that I published then. The reason it was interesting is this was not the standard experimental data for lead telluride. This was experimental data for what was called a very special kind of lead telluride, which had thallium in it, which was thought to change the band structure. But the calculation was not for that, and thallium is poisonous, as you might know. This calculation was for lead telluride with no thallium, only with just sodium or some other inert dopant that doesn't change the band structure. And so it agrees. And what that means is that the thallium didn't change the band structure. And what it really was a manifestation that the band structure of lead telluride is not parabolic and is more complicated than people realized. And so what people thought in the 1960s, when the material was industrialized, is that this is the ZT of lead telluride. And if you dope it as well as you can to get the highest ZT, in the 1960s, it was thought that it behaves like this. This is the best that could be obtained. But what was not realized is that because the band structure is complicated, it's better to put more sodium than people tried. And it was complicated to put more sodium. I mean, it wasn't just because they were lazy, it was because there were issues with the phase diagram that had to be overcome in order to do this. So it was not a scientifically easy thing to do. But anyway, if you just had the right amount of sodium optimized according to the band structure, then you didn't need this poisonous element thallium to change the band structure, but you could achieve this with sodium, and then you could achieve a much higher efficiency. And so lead telluride, in fact, even though it was industrial, was not optimized in the 1960s. An amazing fact, I thought. All right. So the next question is about the thermal conductivity. And so the thermal conductivity in materials like this is controlled by the lattice. In other words, the atoms vibrate, and there are phonons, or lattice vibrations, and these lattice vibrations carry heat. And so understanding the lattice vibrations is what's important to understand the thermal conductivity. And so I wanted to understand more about the thermal conductivity of lead telluride. And so you can calculate the phonons of lead telluride. So this is the plot, similar to the band structure plot. It's in momentum space of the shape of the phonons down here. And what you see, it's a solid. So there's a compression wave. So that's this longitudinal acoustic mode, it's called. This is the compression wave. It's the wave that carries speech in air. It's compression waves. All right. But in a solid, you can also have shear waves that propagate, and these are the transverse acoustic waves. And they also have a velocity. They rise with momentum, but not as quickly, so the velocity is lower. So it turns out that high velocity is good for carrying heat, and so this longitudinal acoustic wave is the one that carries most of the heat. And then there's some other low frequency vibrations, and they are caused by the fact that lead telluride, it's not ferroelectric, but it's near ferroelectricity. So this was all known. So although we did calculations, it was already known. So there was nothing new that came directly from this calculation that we reported. But what was new is that when you do calculations, you can easily change the pressure or the volume of a material. And so if we compress lead telluride, then we got something very different. And so what we got was this longitudinal branch and this transverse branch. You saw those already. Those are the same, more or less. But this other one with these low frequency vibrations moved to higher energy. And that means that when you compress the material, there's a pretty strong interaction between that compression and these vibrations of the crystal lattice. Okay, we compress by 2% and it moves quite a lot. And that must be an anharmonic coupling. And so what it means, remember that this one that carries the heat is a compression wave. It means that there's a lot of anharmonic coupling between this compression wave and these vibrations that correspond to the near ferroelectricity of lead telluride. And so what we concluded from that is that a likely reason for the low thermal conductivity of lead telluride, remember kappa is in the denominator of ZT, is that this ferroelectric mode is strongly coupled to the longitudinal acoustic branch, and that gives the low thermal conductivity. That was the conclusion. So then our colleague did experiments with neutron scattering to see about that. And And this is what he found. I'm not going to go through all this neutron data, but the point is what is seen is a very strong interaction between that ferroelectric mode and the acoustic modes that perhaps can explain the low thermal conductivity of lead telluride. There turns out to be some other factors as well, but it gives some of the explanation for the low thermal conductivity. All right. And so then we try to understand a little bit more about that. And so let's say a little bit more about ferroelectrics. So you know perhaps ferroelectrics. So ferroelectrics are what is used for a medical ultrasound. If you have seen perhaps a picture of a baby before it's born from a medical office, they can image the human baby before it's born, and that's done by acoustic technology because you can't see through skin and so on, and they can then see the health of the baby and advise the mother. So the acoustic technology relies on transducers that convert between electricity and acoustic waves, and those are piezoelectric based on ferroelectric materials. And the material that used to be commonly used was a material called PZT. It's an alloy between lead oxide and zirconium titanium oxide. It occurs in a certain structure called perovskite. Anyway, this is a Nature paper that was published by Ron Cohen in 1992, where he explains the performance of those materials. And it's based on covalency between oxygen and these cations, these nominal cations, lead and titanium. And the way it works is like this, is you have some 2p states of oxygen that are occupied. It's nominally oxygen 2-, and then some empty states on the metal atoms, lead and titanium, that are cations. So these are, for example, the 6p state of lead, which is not occupied. The 6s state of lead is occupied. It's lead 2+. And so that's the ionic story. But then there is some covalency, some hybridization between the oxygen and the lead. And of course, the amount of covalency depends on the distance between the atoms. And so if you change the distance between the atoms, you change the amount of covalency. But what is covalency? Covalency is a mixture of these states, right? So it means that even though the lead 6p state is in principle not occupied because it's a cation, there is some hybridization, some mixture. And so there is some charge on this 6p state, and that amount of charge depends on the distances between the atoms. And so if you move the atoms, you change the amount of charge that's transferred. And so it looks like you're transferring more charge than just the charge on these atoms. And so the so-called Born effective charge is enhanced and can become quite large in these materials. That's how the ferroelectrics work. And we see the same thing in semiconductors. So some semiconductors, this is thallium bromide, I think I'm not going to go through the details, have a similar feature, and it's related to nearness to ferroelectricity. And the important thing is that gives very high dielectric constants. That kind of chemistry gives very high dielectric constants. And that's very good for the semiconducting behavior of these materials. So we see exactly the same thing in lead telluride. And what does good semiconducting behavior means? It means weak scattering of the electrons that gives high conductivity. And we see the same thing in lead telluride. So lead telluride, this is just showing the electronic density of states and showing that even though it's lead 2+, there's quite a lot of lead character occupied. And even though it's tellurium 2-, there's quite a lot of unoccupied tellurium character due to this kind of hybridization that I mentioned before. So what does this mean? This means that we can expect for a certain number of holes, good conductivity in lead telluride, which is important for the thermoelectric performance. And actually, you can see there are many new semiconductors that have very high dielectric constants and are becoming quite important in technology. An example is the perovskite halide solar materials, which also have extremely high dielectric constants, and because of that have very good charge transport, which is important for their high efficiency in solar applications. A big surprise, I would say, when they were discovered, because they are soft materials and have a lot of defects, and still you can collect the holes and you can collect the electrons and make extremely efficient solar cells out of perovskite halides. And the reason is the dielectric constant is very high, and other properties are also favorable. All right. So we see now something interesting. I want to stop now and remind you of what I said before. So remember that high thermoelectric performance is a contraindicated property of matter. And so that means we can expect interesting physics. So I talked about one thermoelectric material, lead telluride. And then you see that lead telluride is actually quite interesting because it connects with quite a lot of things. So remember, it connects with the best piezoelectric materials that are important for sonar and are important for medical ultrasound. It connects with the new kinds of semiconductors like the perovskite halides through the high dielectric constant. It shows very non-trivial band structure that is surprising and wasn't anticipated before, and led to the discovery that an industrial material could have its performance doubled by some simple strategies. So now I come back to the idea of topological insulator. So we saw a connection there. What is that connection? So we came to that by studying a different material, bismuth telluride. Bismuth telluride is an excellent thermoelectric material. It's used in a lot of terrestrial thermoelectric applications. For example, picnic coolers use bismuth telluride generally. Electric picnic coolers. So this is ZT, and this is temperature. And what you'll notice, it's many different materials there are many thermoelectric materials. But it's showing that most of the thermoelectric materials, if you just look at this chart, the ZT increases with temperature, reaches a maximum near the maximum temperature for the measurement, and then falls down. And this maximum temperature is controlled by the stability of the materials. So going to higher temperature helps ZT, and T is inside ZT, so that may not be so surprising, except bismuth telluride. And for bismuth telluride, what happens is the ZT reaches a maximum above room temperature, a little bit above room temperature, and then falls, even though the melting point of bismuth telluride is somewhere here. And so why is that? The reason is known. The reason is that the band gap of bismuth telluride is small, and if it had the same band structure and the same properties, but a larger band gap, the ZT would be higher. And so our idea was, let's alloy with some different elements and see if we can make some better bismuth telluride. And so we thought of selenium, and other people did too. So this is from an experimental group. They made different alloys with sulfur and selenium and showed that, this is Celsius, degrees Celsius. The previous chart was in Kelvin. And showed that the ZT could be high, around 1, for these different alloys at higher temperature where bismuth telluride is not good. But they never achieved this magical material where the ZT just went up. They never achieved that. And we thought maybe the band structure is quite complicated and similar to lead telluride. It could be that it's a matter of properly optimizing the doping level. And so we decided to make some calculations, but we didn't obtain what we expected. So I showed you those isosurfaces for lead telluride, perhaps you remember before. So I just want you to focus on these two. So this is bismuth telluride, and this is bismuth telluride with selenium. And you can see these isosurfaces are quite complicated. In other words, they're not spheres. A parabolic band would give you spheres. Oh. But it's not. And so So you could sort of say qualitatively, okay, well, he said before that complex band structures are needed, something other than parabolic. So maybe that's the reason, is that it's a good thermoelectric. And he also said that he wants to find a material that has a larger band gap and is similar. And then you look here and say, yeah, it's also complicated. But if you look more closely, you can see it's also very different. So in a way, this failed because we didn't keep the same band structure. And just to show it better, this is one, this is the other. They are both complicated, but they are different. And because of that, we could not, if we could keep this and increase the band gap, then we could obtain the highest CT. But we couldn't. And so why is that? Why is it so sensitive? If we take some of the tellurium and replace it by a very similar element, selenium, according to this, the band structure changes very, very much. Why is that? And so then that leads us to the topological insulator. So what is the topological insulator? And people wondered about that because I showed you that review article, remember? And in that review article, it seems like that there was a very strong connection between topological insulators and thermoelectric. That's a fact. But why? Nobody could solve that. And the reason is that it's not very simple to understand because what is a topological insulator? This is from Wikipedia. You have a semiconductor with a valence band and a conduction band. And then on the surface, you have some special electronic states that are topologically protected and have low scattering. And so if your Fermi level crosses those states in the band gap, you can observe those. And so here is some experimental data. But the trouble with that explanation is that for thermoelectrics, is that for thermoelectrics, the Fermi energy is not here. It crosses either the valence band because we need some holes, or the conduction band because we need some electrons, and we need to optimize that. And we optimize that by having the right number of electrons or holes, not this intrinsic material. And secondly, the thermoelectric performance is a bulk property, and these are about surfaces. And so it's not about the surfaces. And so why should there be a connection? And nobody knew that. So here again is a schematic of a band structure. And how do we get a topological insulator? We can imagine, this is a cartoon. We imagine we start with parabolic bands, an ordinary semiconductor. There is some interaction. The interaction could be just having relativity, which lowers some states with respect to others. And then that causes the bands to cross. So then that becomes like a semi-metal, and that's called band inversion. That's necessary in order to get a topological insulator. And then there's some other interaction that stops these bands from crossing. That can be spin orbit, as it usually is. And so a gap opens. And so now we have our topological insulator, and depending where these crossings are, the topology can be different. But the basic story is this has the character of the old conduction band. But then the character for the old conduction band occurs here. And this has the character for the old valence band from here. And so there's a change of character, and there can be a topological aspect to that here. But the other thing you notice immediately is that this was parabolic bands, but the shape of this band is not parabolic. It has this W shape, right? And so this is very much not parabolic, and that's very much good for thermoelectrics. And so there's the connection, is that in fact, this band is quite complex, and that's good for thermoelectrics. And so in general, we expect topological insulators to have complex, not parabolic band structures. And that's a good thing for thermoelectrics. And we realize that. And that also explains why this methyrite and this alloy, or this compound, are not similar. The reason is that we imagine turning on this interaction, spin orbit in this case. As we do that, we see the bands approach, they cross at some critical point, you get the band inversion and something very complex, and you're quite close to this critical point. And here's something else complex. The critical point is in a little bit different place. And because the details of this depend very strongly on this critical point, then it's very sensitive to where is this critical point. And so there's a very strong sensitivity. And that's why those two things are different. All right. So I'm almost done. I think my time is also almost up. And so I want to finish with one more thing, and then we'll be done. So I talked about the electronic complexity as being important, but I kind of presented this in a very qualitative way. But we are physicists, and we want numbers. And anyway, if you want to make applications, you need numbers. So it's not just about some material has a complex band structure, and that's good, but it's about which material is better than which other material. And so we need to be able to look at this complexity of the band structure and understand what's better than what. And so there's this carrier pocket complexity, and this can play in different ways. We could have multiple carrier pockets. This is magnesium antimony, a very interesting recent experimentally discovered material that was previously theoretically predicted as N-type, and kind of dismissed by experiment as saying it's impossible to achieve N-type. And then some experimentalists tried hard and achieved N-type and showed it was a very good thermoelectric. You can have other kinds of complex band structure. This is a concept called band convergence, where you have multiple bands that come close in energy and then can yield complex band structures. This is some other kinds of isosurfaces that come from degenerate bands, and so on. Here's just another material with very anisotropic carrier pockets, silver, bismuth, selenide. So what's better than what? How do we know? And so here are some other mixtures. We wanted to have a metric. And what do we want to measure? So we saw the problem of thermoelectrics was this contraindication, so that sigma, the conductivity, and the Seebeck coefficients are coupled, because in a parabolic band structure, they're tied together. So we want to have a non-parabolic band structure, and we want to figure out the extent to which these quantities are decoupled in a given band structure. And we want a metric that depends on temperature and doping level so that we can optimize those things. So we wanted to find a screen that we could apply to band structure. And so what we came up with was a so-called fitness function. And this is the fitness function T. So we wanted something that you could easily calculate from the band structure with the codes that people have. And so you can easily calculate something called sigma divided by tau. This is the conductivity, but without the scattering time. So it's just a band structure quantity. This is the Seebeck coefficient that I showed you before. You can calculate that. And N is the density of states per unit volume, which you can also calculate. And this 2/3 power is in order to achieve a behavior that would be consistent with what's expected for electron phonon scattering, with some modification that I'm not going to discuss. But we just tried it. So this is this function T that you can calculate from the band structure. This is carrier concentration, but what we did was we calculated T at 800 Kelvin for P-type and N-type materials. And we calculated it as a function of doping level, and then took the highest value and plotted it here. So this is lead telluride. It's plotted. This is the value of the carrier concentration where it occurs. Remember, this is a higher carrier concentration than people experimentally did in the 1960s, but it's very close to the one that now is thought to be optimal. So T gives you this optimal carrier concentration, and we plotted it. Okay, so you can do that, and we find some interesting things. As we find, for example, that cubic germanium telluride is fine. Okay, so we can find some compounds that way. And I just want to mention cubic germanium telluride. That was another material that experimentalists thought could not be made because at 600 Kelvin, where it's really good, it's not cubic. So what's the point of calculating a cubic material in the temperature where it's not cubic because it's rhombohedral there? But still, it's tempting because this fitness function is very high for cubic germanium telluride. So we discussed that with experimental colleagues, and we discussed the reasons. I'm not going to discuss them, but they did it. They alloy some manganese, and they find out that manganese can make it cubic. It also makes a lot of scattering, but still the ZT is very high. So they find a material with a high ZT over a wide temperature range by making germanium telluride cubic. All right. So I think I'm going to, this is some other material that we identified. This is monolayer palladium diselenide. It was an unknown material, but we predict that. And we found it was interesting, not so much for thermoelectric, but we studied it because we thought it might be an interesting thermoelectric, but then people make it. So I just want to have this, and they find it very interesting for other applications. So you can predict things, and nowadays experiments are good and they can make things, and sometimes you get lucky and this stuff turns out to have some use. But really what I want to do now is I want to wrap up because I think my time is up more or less. And I want to just give you some ideas. So I have some summary here on this slide. I'm not going to read it. But I want to give you some ideas, and especially I hope young people will listen to these ideas. I know young people may have their own ideas and their ideas may be better than my ideas. That may very well be the case, but let me give you my ideas because that's what I have. So first of all, I want to point out that an industrial material from the 1960s that was used, and therefore there was an economic benefit to optimize it, was not fully optimized. And so that's a failure of the technology from that time, and it was readily done nowadays after theory. And why was this? And the reason was that the textbook model was the parabolic band model. Students learn the parabolic band model, and it's a simplification, but they learn it. According to the parabolic band model, which has many parameters, you could not get a higher ZT in lead telluride by increasing the amount of sodium. But you could. But according to the parabolic band model, you could not. And so since it was hard, people didn't try it. And what went wrong is they listened too much to theory without carefully considering all the possibilities. So don't listen too much to theorists. I say that as a theorist, but pay attention. Okay. So the other side of that is magnesium antimony, which was discovered after people said it was more or less impossible. Theory said it could be a very good thermoelectric, but experiments said magnesium is volatile and it will always be p-type and not n-type. But then some people in a company decided to carefully seal tubes and try to synthesize n-type magnesium antimony. And then they discovered a very remarkable and useful thermoelectric material. So do listen to theory sometimes. And then finally, there is this theme of contraindication, that there are connections between many different things. And so always pay attention to the possibility of other things. So you may be looking for better thermoelectric materials in order to make better cars. But if you are lucky, you can discover something very important and novel, such as topological insulators. So always try different things, look for connections between things, and then you may discover something very interesting. So with that, I'd like to finish my talk. Thank you.
Professor, really it is very interesting, Professor. Really you have explained this keenly and slowly. We are very impressed. Thank you, Professor.
You're welcome. It's my pleasure.
Thank you. Thank you very much. Wonderful presentation, Professor.
Professor, one request, Professor. Can you please share your Wikipedia page, Professor? Please.
Share what should I share? Unshare? Stop sharing. I
Yes.
should stop sharing. Okay.
Yes, yes, Professor. Wikipedia.
Okay.
You please share your Wikipedia page, Professor.
My what page? I'm not sure if I understand. You want me to show what?
Oh, your Wikipedia page, Professor.
Oh, Wikipedia. Oh, I have to find that. Just a second. Let me see if I can find that.
Jayalakshmi, you can.
Yeah. Yes, yes.
Okay. I don't have that handy.
She will.
but
She
let me
will know.
look
She
for
will
that.
know.
Maybe I can find that. All right. Okay, I find it. Okay, I find it. Okay, I can share it.
Okay,
All right.
Professor. Okay.
Let me try to share that. Just a second. So share screen. Let me see if I can share screen share. So, all right. Okay, it should be shared now. Is it right?
Yes.
Yes, Professor.
Okay.
You are so simple.
So it shows my age. I see.
You don't look so.
So what I could say is, according
We
to this.
we are seeing only your credentials, not your age.
Okay. Well, according to this, I was born in 1958, but that book by Yaffe on thermoelectrics was from 1957.
Wow.
So thermoelectrics is older than me.
No.
Nice, nice.
So, dear
We are all
participants,
blessed today to listen to you.
Oh, thank you. You are very kind.
Yeah.
so dear participants, if you have
Madam, please mute, ma'am.
muted, ma'am. Dear participants, please post your doubt in the chat box, or you can raise your hands and you can ask your doubt.
Good evening, Professor.
Okay, I'm going to stop this sharing so that I can see you. Yeah, so
Join with video and ask question.
Dear participant, please join with video and ask question. Please.
Okay, I see one question in the chat.
Yes, Professor.
So the question in the chat that I see is from Dr. Amar, and it says, normally mobility increase with increase in temperature. Under what circumstances mobility increase with decrease in temperature? So mobility can behave in different ways in semiconductors. So in the usual semiconductor devices that we think of, they're not so heavily doped. There can be some exceptions, but maybe more intrinsic semiconductor. And in intrinsic semiconductor, what can happen is the conductivity increases with temperature. That's what happens usually. And the reason is because the number of carriers, the number of holes plus the number of electrons is a constant. But both of those, or the number of holes minus, if you like, the number of electrons, if you don't count the sign of the charge. And so the number of carriers increases with temperature, depending on the band gap. And so the conductivity increases. But what happens in thermoelectrics is they're more like metals because they're doped very heavily. So they're what's called degenerate doped. In degenerate doped semiconductor, the number of carriers doesn't change with temperature. And instead what happens is the carriers scatter. And an important part of scattering in semiconductors that are used for thermoelectrics with heavy doping, it's not the impurity scattering, it's the electron phonon scattering. And so when you heat the material, the atoms vibrate more. And so the number of phonons increases and the scattering increases. So the result in thermoelectric materials, which is a little bit maybe different, is that the conductivity decreases with temperature. And the reason is there is more scattering from the phonons. And that's true for both N-type and P-type thermoelectrics. Does that answer your question?
Professor, one more participant raised her hands. Celestina, you can ask your doubt.
Yes, ma'am. Good morning, Professor. I'm Celestina. So in thermoelectrics, if we introduce some complex crystal structure, so by that we can increase the figure of merit. But some materials like tin telluride and some of few materials, they are having a basic cubic structure. Okay, so they are also giving a good a figure of merit. So why is that so, Professor?
Well, that's a very good question. Thank you for asking that. I think that also says something very interesting about condensed matter physics or material science. I'm very grateful for that question. Thank you for asking that. So we want to have for thermoelectric below lattice thermal conductivity. So if you make the crystal structure very complicated, then there's a lot of chance for the lattice vibrations to interact with each other because of the folding of the Brillouin zone and other reasons. So complex crystal structures generally give low thermal conductivity, and low thermal conductivity is very good for thermoelectrics. And so looking for complex crystal structures is one very active and very fruitful way to find good thermoelectric materials. But then there are some other materials. Lead telluride is one example, and tin telluride is another one, where they have low thermal conductivity, even though the crystal structure looks quite simple. So it's sodium chloride structure for lead telluride and tin telluride. So why is that? So it turns out there's many ways to get low thermal conductivity, and so this nearness to ferroelectricity and strong anharmonicity is another way to get low thermal conductivity. So that's the reason why those materials could have low thermal conductivity. But more generally, it means that when we work with condensed matter, we work with an enormous number of compounds that can have different physics and very interesting physics in different ways. And so when we want to achieve something, there can be more than one different mechanism that we could use. So we could try different approaches, and both of them could be valid. So the idea of complex crystal structures is a valid approach that gives new and useful materials. The idea of simple crystal structures near instabilities like ferroelectricity is also an approach that yields new materials and interesting thermoelectrics. And more generally, what it means is if you think maybe you can find some other mechanism that people haven't considered before, then some new direction in materials.
Professor, one more question in the chat box. Is it possible to increase the band gap of bismuth telluride for high temperature application?
Yes, so what Zifeng Ren's group showed, and what our calculations also showed, is that the band gap will increase if you alloy with materials like selenium. The band structure will change. So you can obtain a higher band gap for higher temperature application, but the ZT is around 1. So the ZT doesn't keep increasing with temperature. So you obtain a higher band gap, but you also change the band structure. And so you can obtain a good thermoelectric material at higher temperature that way. But you cannot obtain, at least as far as we know so far, a material that has an extremely high ZT that way because the band structure also changed. Perhaps somebody will find some different approach and make that work, but so far it's not been achieved, as far as I know.
Professor, one more question. Can you give your suggestion on how to improve thermoelectric properties of metal oxides like zinc oxide?
So yes, so I worked on zinc oxide before, and I think oxides are very interesting for thermoelectrics. The ZTs achieved in oxide so far are are around 1, which is less than what has been achieved in some other materials like chalcogenides. But still they are very interesting for several reasons. First of all, oxides have some distinct advantages for processing and for use in the environment. And secondly, many oxides can extend to very high temperature that are not achievable in other materials. And zinc oxide is a material that can extend to very high temperature. So people have done a lot of optimization of zinc oxide. I think in a material like zinc oxide, there are several strategies. One is to try to find ways to lower the thermal conductivity more, which I think might be possible to do. Another way is to pay a lot of attention to the doping levels and to optimize the doping levels carefully for different temperatures. And finally, when we think about oxides, one way is to think about the application, because there's many different applications. So if zinc oxide is best at very high temperatures, then it may be best to try to optimize it with a view to the applications that are at very high temperatures. So to think of very high temperature applications and to try to find a match between the material and the application, that can also be a way.
Professor, one more interesting question in the chat box. Sir, do you think the thermoelectric will be able to create advanced medical devices in order to compete artificial intelligence in the near future?
So I think that's a question of human imagination, because when you say able, I think human beings are able, and in technology, there are things that are amazing to me that are real, that come, that when I was a child, I couldn't even imagine. And so, and are now part of everyday life. So I think that medical technology, of course, will advance very much. Thermoelectrics give ways of doing things that are important for medical technology. One of the things that you may not realize is that medical diagnostics rely very heavily on thermoelectric technology, because thermoelectrics, besides energy conversion, they give you a very good way of temperature control, which is important for just tests that for example, blood tests. It's necessary to do reactions at very carefully and precisely controlled temperatures. And this we do with thermoelectric. So they are used for this. Measuring temperature very precisely in medical context also can be done with thermoelectric. So they're already used, and I'm sure people will think of other important applications for thermoelectrics in medical contexts. I just don't know them.
Thank you so much, Professor. Patiently you have answered. Yes.
I have a question, ma'am. Professor, so to find a Seebeck coefficient, we are making this material into bulk. Okay, so why is that so, Professor?
People have discussed nanomaterials for thermoelectrics, both nanomaterials that are made into bulk by assembling them, like sintering them together, but also like monolith, like thin films people discuss, and nanotubes people discuss, and various other materials. They have different applications, of course, because if you think about a car, then you are probably thinking of a bulk material because you have a lot of heat and need a lot of electricity, and so you are thinking that there may be nano applications of heat manipulation, and people think about that. For experiments, the nano applications are more difficult, and the reason they're more difficult is it's difficult to control temperature gradients at the nanoscale, and it's difficult to measure them. And so when you characterize a thermoelectric material, you need to make measurements. So you need to apply temperature gradients and measure thermal conductivity. You need to measure Seebeck coefficients, and all of those require different technologies at the nanoscale. People work on that, but it's most activity right now, I would say, is in bulk materials, because the applications are simpler and the measurements are more standard.
Thank you, Professor.
Professor, thank you so much, Professor. You have patiently answered the questions, and we are blessed to hear your lecture, Professor. Thank you so much. Now I request Dr. K. Subramaniam, Assistant Professor, Department of Physics, to propose the vote of thanks, Professor. Subramaniam, sir.
Hello, ma'am. Am I audible to you?
Yes, sir. Yes, sir.
Okay. Good evening, all. On behalf of the management and Department of Physics, SRM IST Ramapuram campus, Chennai, my heartfelt thanks to Dr. David J. Singh, Professor, Department of Physics and Astronomy, University of Missouri, Columbia, USA, for delivering a wonderful lecture on understanding thermoelectric and their performance. Professor, really I admire on your patient lecturing. So very good, very nice presentation. Thank you, Professor, for spending your valuable time with us. And my sincere thanks to our chairman, SRM Group of Institutions, Director, Dean ENT, Vice Principal Academic Administration, SRM IST Ramapuram campus, for your support to make this event to be a successful one. Last but not least, I thank all the participants who have actively participated in this program. Thank you very much.
Okay, thanks to everybody.
Thank you.
Thank you, Professor. Thank you,
Thank
Professor.
Thank you. Good night.
Good night.
Have a good day.
Thank you.
So, dear participants, feedback link is available in the chat box. Kindly use it.
close it.